Laplace transform is a powerful mathematical tool that is the number one choice in stability analysis and control system. Its power lies in its ability to convert the calculus representation of an ordinary differential equation to the algebraic representation. In this video, you will find an explanation about the Laplace transform, in particular about its derivation from the Fourier transform, impulse response, region of convergence, and the basics of pole zero plot. This video is the first of several videos about Laplace transform. The core of Laplace transform lies at this simple yet profound integral. It looks like the Fourier integral, but the frequency omega is replaced by s. To understand the reason behind the shift from j omega in the Fourier transform to s in the Laplace transform, let me give you an example. Put the time domain function x of t as an exponential function that is non-zero after time t equals 0, but instead of decaying, its amplitude grows. If you try to do the Fourier transform to it, the integral will not converge. The Fourier transform cannot handle growing exponential function. Luckily, there is a way out of this dead end by introducing a real component to the game. So instead of j times omega, you have sigma plus j omega. With this, the integral goes through an amazing change. The integral will converge when sigma is greater than 1. As the animation shows you, the existence of the real part sigma causes the blow up in the growing exponential. We can simplify the term at the exponent of the kernel by introducing s. With this, we finally have our Laplace transform. If we apply this to the growing exponent, we finally arrive at something. Laplace transform can handle this because s, or the complex frequency, has real and imaginary component. Its real element is sigma, and imaginary element j omega. To apply Laplace transform onto the problem of ordinary differential equation, we should first build a tool that is indispensable for our next work. The system that will be our test toy is, surely, the mass-spring system. Given a function x of t, how do we calculate the Laplace transform of its first and second derivative without explicitly calculating the Laplace transform of xt? Let us do this for x prime t first. Okay, that's for the first derivative. Now let's move on to the second derivative. It's a little bit more involved than the first derivative. Impulse response is measured at the system's output when a delta impulse is thrown to the input side. To illustrate this, consider a square pulse with duration 1/2 and an amplitude of 2, which clearly implies that its area is equal to 1. This pulse gives a short burst of energy to the mass, so it swings for a while before coming to a standstill. An impulse input happens when the duration is compressed until it is very close to 0. Consequently, the peak becomes so tall that it approaches infinity. At this point, the square pulse has become a delta impulse. Because the area remains at a constant value of 1, the result of its integration with respect to time is also equal to 1. Before stepping into more rigorous calculation, let's build some intuition about the impulse response. We return to our square pulse. The pulse is turned on for a brief moment, then turned off. When the pulse is on, the displacement goes to a particular distance, then after the pulse is turned off, it steadily shrinks to 0. When the duration of the pulse is shortened more and more, the same behavior occurs. Eventually, we reach a point where the pulse becomes a delta impulse and the output becomes the impulse response. Are you ready for some deep calculation? First, we write the differential equation, then we put the delta impulse at the right-hand side. Using the tool that we have constructed, we can calculate the Laplace transform of that ODE. Anyway, the Laplace transform of the impulse input is equal to 1. We ignore the initial conditions because, for the impulse response, the system departs from the condition where it has no energy. Looks pretty good, isn't it? The impulse response usually takes a symbol capital H of s. Its time domain counterpart is small h of t. To get there, we must take the inverse of the Laplace transform. For the sake of simplicity, we shall give numerical values to its parameter, which is zeta equal to 1 and omega n equal to 4. multiply h of s with e to the power of st, and integrate it. Unfortunately, its inverse Laplace transform is very hard to compute, so I only show you the end result and the plot. For this kind of calculation, we usually resort to Laplace transform table instead of direct computation. You might remember that earlier in this video, we used a growing exponential function as an example to demonstrate why we need the Laplace transform at the first place. Its Laplace transform is quite simple, with the denominator being equal to s minus 1. This system is said to have a pole at s equal to 1. For now, just consider a pole as a point where the denominator becomes 0. More explanation will come later. Let's draw the pole at the complex domain. And you might remember that the Laplace integral only converges for the real part of s greater than 1. We can draw the region of convergence, or ROC, in the complex domain by shading the region where the real part of s is greater than 1. ROC is not just some random area you shade, but rather it is about a kind of identity. Consider another signal which, instead of growing in the positive x and y direction, it decays in the negative x and y direction. Surprisingly, the Laplace transform is the same. Now we have a new problem: how to tell the difference of one from the other. The answer lies in the region of convergence. This time, because we are integrating from minus infinity to 0, the real part of s must be less than 1 for the integral to converge. This different ROC now has become a tool to tell the difference between those two results. It's a signature of the signal's personality. The signal on the left side is called the causal signal, propagating from left to right, where the one on the right side is called the anti-causal signal, propagating from right to left. This is the end of part 1. I'll let you know when part 2 is available. Please support us by subscribing to this video. Thanks for watching and see you next time.